This is an equilibrium example problem. The problem asks us to calculate the enthalpy of reaction under standard conditions and the entropy of reaction under standard conditions for the reaction of nitrogen gas plus oxygen gas forming two molecules of NO gas, and we're given some equilibrium constant values and some temperatures, and then we're asked at what temperature does the value of the Gibbs energy of reaction change sign. So the first thing I want to point out is right here, the equilibrium constant is divided by 10 to the negative 4, which means that at 1900 Kelvin, the K value is 2.31 times 10 raised to the power negative 4. So the first thing that we actually have to do is convert these equilibrium values into their real numbers, and that dividing by 10 to the negative 4 just makes it easier to actually type it into the table so the table takes up less space. So the first thing we have to figure out is how in the world from equilibrium constant can we get enthalpy and entropy? Well, we know that the equilibrium constant is equal to the Gibbs energy of reaction, so let's start there and see what happens. The Gibbs energy for the reaction under standard conditions is equal to negative RT times the natural logarithm of the equilibrium constant. We also know that the delta G for the reaction is equal to the enthalpy of the reaction under standard conditions minus T times the change in the entropy for the reaction under standard conditions. So it looks like I have a way of equating the equilibrium constant to the enthalpy and the entropy. I want this equilibrium constant by itself, so I'm going to divide both sides by negative RT. And I'm left with the natural logarithm of the equilibrium constant is equal to negative enthalpy of reaction under standard conditions divided by R. I'm going to separately use 1 divided by the temperature because that's the other variable I'm given. And that is, I add in the entropy of the reaction divided by R. Now, when I put this into Excel using the natural logarithm of KEQ as Y, this term is my slope, this is my X, and this is my intercept. I discover that the equation is Y is equal to negative 2156X plus 3.0761. So here is my value of the entropy divided by R, and this is my value of the negative enthalpy of reaction over R. So I can extract the enthalpy of reaction and the entropy of reaction. So the negative value of the enthalpy of the reaction is divided by R is equal to negative 2156. And actually the units on this are Kelvin, because I'm dividing by 1 over Kelvin because it's Kelvin down here and it's the rise over the run. And so the positive enthalpy of reaction is equal to 2156 Kelvin times R, which is 8.314 joules per mole Kelvin. And that's equal to 17,900 joules per mole. I can do the same thing over here. My reaction entropy change is equal to 3.0761 times R, which is 8.314 joules per mole Kelvin. And that's equal to 25.6 joules per mole Kelvin. Now, if I want to know at what temperature the Gibbs energy of reaction changes sign, that's when it's equal to 0. So I'm going to come back up to this equation and say 0 is equal to the enthalpy of the reaction minus T times the change in the entropy for the reaction. And so T is equal to the enthalpy of the reaction minus the entropy change of the reaction. And that turns out to be 699 Kelvin, because I'm going to take this one over to this side and then divide by the entropy. And so anything above this temperature or below this temperature, depending on which way this inequality works, will change the sign of delta G because it goes through 0.